Okay, good afternoon. Let's get started. So first of all, you have noticed that we have created the assignment about the project option. So please make a decision as soon as possible. And our midterm report due is expected to be the week after the spring break. So that means after the deadline of your project option, you got like 1 month, a little bit more than 1 month to do the preliminary things about your midterm. But if you can make a decision early, you can start early. Okay, so oops. And if you're still not sure what kind of thing you would like to do, right? Or what kind of project you want to do, or can be viewed as a good choice. Feel free to come to the office hour. You can talk to our TA or talk to me. Right? Okay. So let us continue with the exponential family. So in the last lecture, we started introducing a broad family of distributions, which is called exponential family. Okay? So why are we interested in exponential family? Because this is a family of distributions share the same kind of nice and convenient structure, which are critical for us to conduct simple inference techniques, like, for example, the variational inference or the message passing. The key idea of those approximate inference is to approximate the target posterior distribution with some simple distribution. What kind of simple distribution? We often use some exponential family distribution. Right? That's why this is important, right? Because once you know what is the general properties of the exponential family, you can leverage these properties to simplify the computation. So, in general, if we say the random variable x follow a distribution in the exponential family, where the distribution itself is parameterized by the parameter eta. So eta here is often called natural parameter. Then the density of this distribution has the following form. Okay, so first we got h of x here. So h of x is a function of x, which has nothing to do with eta. So it just gave you some like actual flexibility that you want to introduce some component out of control of the exponential family. But in most cases, you can just set h of x to be 1, a constant. And then the case structure is this exponential term. So in the exponent of this exponential term, we see a linear structure, a dot product between a function of the x, we call it u of x, and the natural parameter eta. So the u of x is really viewed as a vector. So it's a multi-output or vector output function. It takes the input of x, so you can view that, okay, I do some kind of transformation over x. I got some kind of transformation of x, we call it u of x. Then I do the inner product or dot product between ux and my natural parameter eta. Then I take exponential to this dot product to represent the strength of this density. That's the case structure. Then if we take a look at the z of eta, so what is its role? What's the role of z eta? Yes, normalizer, right? So I need to ensure that, okay, if I just integrate the density over x, right? This is density of x, this integration should be 1, right? So of course, I need some normalizer to ensure that point. So z of eta is the normalizer. And this normalizer obviously is a function of eta, because when you do the integration over x, right? X, it just disappears, right? The whole integral is determined by eta. That's why the the normalizer should be a function of eta. Does it make sense? So, and u of x, which is a transformation of the random variable x, are usually called sufficient statistics. This is kind of consistent with the definition we introduced before, because we will have a set of data like x1, x2, I mean observation of x. Right? If we want to estimate the parameters of this distribution like eta, and you see that okay, you only need to memorize the transformation over each observation, like ux1, ux2, ux3, and so on. So that means if you can keep and store those transform observations, it is enough for you to get a maximal likelihood estimation or MAP estimation of the eta. So that's why it's called sufficient statistics. Does it make sense? And oh, sorry. I don't know what happened here. Okay. It's kind of bothering me. I'll try this again. Okay. So eta here, again, it's called natural parameter. Why it's called natural parameter? Later we'll see. Actually, many distributions commonly used exponential family distributions, their parameters which you're familiar with are not natural parameters. They are usually called mean parameters, like Gaussian distribution. Later we'll see that the most touchable or most commonly used parameters are mean and the covariance, right? But you got to map it to the natural parameter when you view it as exponential family distribution. And z eta, as we just mentioned, is called normalizer function or partition function, which is computed by the integral of the numerator, right? And because this integral h of x is exponential term, when you marginalize out x, right, x disappears, is only determined by eta, so it's a function of eta. So another commonly used form that, okay, why should I explicit write down a denominator, right? Why not just put my normalizer into the exponential term as well? So then you can see another common use form, like I can take this guy as e to the logarithm of 1 over z of eta, right? So that I can put, I can merge the exponent together, right? Then we get this form, h of x, and just one exponential term. The exponent is dot product between the sufficient statistics and the natural parameters, and subtracted by the logarithm of z of eta. So log z eta is called log normalizer or log partition function, which is very, very important. And you later will see many properties of the exponential family actually comes from or is contained in this log normalizer. So now let us look at some concrete examples, right? What are the common used distributions or exponential family? Exponential family. The first example is the Bernoulli distribution. Okay? So we discussed about at early beginning, right? So the common form of the Bernoulli distribution, x, remember x here is a binary, right? Either 0 or 1. So Bernoulli distribution is usually to model, okay, when you toss a coin, what's the chance that you see a heads up or tail up, right? So x is observation, which is either 0 or 1. And the sorry, and the distribution is parameterized by this mu parameter. Mu is between 0 and 1, indicates the chance that you see x equals to 1, right? So the probability of you observe x in the Bernoulli distribution is mu to the power of x times 1 minus mu to the power of 1 minus x. Right? So now if we want to convert it to the standard form of exponential family, what shall we do? Any thought? or how can we connect it to the exponential family? There. Yeah, we try to remember the exponential family is some exponential form, right? Eta transpose u of x subtracted by log normalizer, something like that, right? So let us first try to represent the whole probability in some exponential form. How can we do that? We take a logarithm and take exponential. That's it, right? So we can do this. So you can see that we take logarithm over this guy, becomes x times logarithm of mu plus 1 minus x times logarithm 1 minus mu, right? And then I need to take exponential in outside to be equivalent to the original form, right? And then we just take a look at the exponent, right? And we just merge all the terms related to or involving x, right? So it's relatively straightforward, right? You got two terms that contain x log mu minus x log 1 minus mu, right? So if you just merge them together, you get x times logarithm mu over 1 minus mu plus logarithm 1 minus mu, right? And then if we just put this constant outside of the exponential, right? You multiply e to the power of logarithm 1 minus mu, right? You got 1 minus mu e to the power of x logarithm mu over 1 minus mu. Right? So then we just contrast to the general form of the exponential family, right? So the general form of exponential family has this form, right? And this is the form of Bernoulli distribution we just derived, right? So now we can see clearly Bernoulli distribution is a member of the exponential family. Right? So what is h of x? Let us just look at here, right? What is u of x? What is the sufficient statistics? Any thought? It's just x. Yeah, there's no trap here. Yeah, just the obvious observation, right? So just x. And where is eta? This guy, right? Log mu over 1 minus mu, right? The guy who just multiplies with x, right? And remember here, in the general case, well, ux is a vector, eta is a vector, right? In this Bernoulli distribution, of course, ux and eta both become scalars, so become numbers, right? So that's why you can see x is ux, and this guy is eta, and their dot product is just both terms like together, right? And then what is h of x? It's simply 1, right? And normalizer is just here, right? Normalizer is 1 minus 1 over 1 minus mu, right? And it's just mapping, right? Just mapping. So we can obviously see by contrasting the form we derived, the equivalent form we derived and the general form of exponential family, it's pretty straightforward to say that, okay, my sufficient statistics is x, h of x is simply 1, okay? And the normalizer here, yeah, let us first look at the natural parameter eta, which is logarithm mu over 1 minus mu. Okay? And then z eta, we know that, which is 1 over mu, right? But as we mentioned, right, in the exponential family distribution, we want to represent normalizer z in terms of the natural parameters. Right? So now we know that the natural parameter is essentially a transformation of the mu parameter, right? Right. Natural parameter eta here is logarithm mu over 1 minus mu, right? And z, when it is represented in terms of mu, is just 1 over. If we want to represent z in terms of eta, it's just then represent z correspondingly, right? So you got 1 plus e to the power of eta. Does it make sense? Right? It's just a little bit work, like you have to solve mu in terms of eta, right? Well, I forgot what's the, but you can do this like e to the power of eta equals to mu over 1 minus mu, right? Then you can solve mu in terms of eta, right? And then you just substitute for mu, right? Substitute for mu, you get a form of z of eta. Right? Does it make sense? Yeah, I believe this mapping or transformation is kind of straightforward. Any question? Okay, so now I want you to take a look, right? So we can observe that actually you rarely use this form to express a Bernoulli distribution, right? Although it is equivalent, right? The most commonly used form for the Bernoulli distribution is actually what we wrote. Sorry, it's here, right? And we believe that, or we by default assume that, okay, this is a distribution of Bernoulli and it's parameterized by mu, right? Actually, it's the mean of the random variable x, right? X, remember, x is a binary 0 or 1. The mean of x is actually the probability that x takes 1, right? So it's mu. So you can see that. So for this Bernoulli distribution, the common use representation are represented by the mean parameter mu, right? Is represented by mu to the power of x, 1 minus mu to the power of 1. It's parameterized by this mean parameter mu, right? But when we convert it to the exponential family, oops, when we convert it to the exponential family, that actually you represent the whole distribution in terms of natural parameter, right? And also your normalizer function is also the natural parameter. So you can see that actually there's a mapping between the mean parameter and the natural parameter. Does it make sense? Right? So let's keep this. Let's keep it in our mind, right? Let us continue. Right? So second commonly used example in the exponential family is multivariate Gaussian distribution. Right? So this is where we see the density of the multivariate Gaussian distribution, right? So it is by default we assume it's parameterized by mean and covariance, right? Mu and sigma. The density is the determinant of 2 pi sigma to the power of minus half. Then you got exponential term, right? The exponent is minus half x, this quadratic term, right? So now let us try to convert it into a standard exponential family distribution, right? So this is a relatively straightforward because in the Gaussian distribution itself has already contained an exponential term, right? So what we need to do is just expand the quadratic form and then extract out the terms that contain x, right? So it's straightforward that you can derive. Well, you got exponential term. In the exponential term, the exponent that relates to x, you only have 2 terms. One is this trace minus half x transpose sigma inverse. The other is a linear to X, right? X transpose sigma inverse mu. Right? And of course, you got some other terms, which is also exponential term, but doesn't contain X, which is e to the power of minus half mu transpose sigma inverse mu, right? And it's 2 pi sigma determined to minus half. Right? So you can take a look at like what kind of sufficient statistics can we extract from this form. So see that actually, you know, multivariate Gaussian distribution, we did two transformation of X, right? One is X itself, okay? One is just X itself. The other is actually half X transpose. So you can see that, okay, I give me X, right? I give you two outputs. One is X, one is half X transpose. And correspondingly, our natural parameter will be sigma inverse here, which corresponds to this half X transpose, and sigma inverse mu, which corresponds to X. Right, you might be confused that, okay, where is this eta transpose UX come from, right? Or let me write it in the original order, like UX transpose. Where does this come from, right? So don't worry, like because this is a trace term, right? Although this guy is a matrix and this guy is matrix, and if you do the trace term of two matrices, right? The multiplication of two matrices, trace of A transpose B, it is equal to the dot product. So essentially they're equivalent to, okay, I'm gonna transform X to these two terms and then vectorize them. Product of the vectorization of the eta here is the same thing. Does it make sense? Any question? Right. So then we now know that, okay, we got our sufficient statistic U of X, right? Which includes X itself and a quadratic transformation of X and eta. And the remaining terms are related to the normalizer, right? And again, h of X is simply 1. Okay? So Z of eta will be the inverse of this guy. Remember, Z of eta is in the denominator, right? So you should take the inverse of this factor outside, right? So it's 2 pi determinant of 2 pi sigma to half e to this half mu transpose sigma inverse mu, right? So in this way, we can also see that the multivariate Gaussian distribution is also belongs is also a member of exponential family. Okay? And then we got our z eta, right? And z eta here, like if you represent z, the normalizer in terms of mu and sigma is in this form, right? But according to our definition, right, we know that this is our natural parameters, right? We got two natural parameters. Okay? One is sigma inverse, the other is sigma inverse mu, right? So if we want to represent the normalizer z in terms of eta, we need to do a little bit more transformation, right? You need to represent sigma and mu in terms of the terms eta inside eta, right? So here eta 1 is sigma inverse and eta 2 is sigma inverse mu, right? So in this way, you can represent sigma inverse is eta 1. Sorry, we'll represent sigma is sigma 1 inverse, and mu is sigma 2 times is eta 2 times sigma, which is sigma 1 inverse, right? Now you just represent, you could just substitute sigma and mu for their representation in terms of eta 1, eta 2. Accordingly, you will eventually get the normalizer in terms of natural parameters. Does it make sense? Right? So if you still feel like I didn't catch up, every detail is totally fine, right? Again, after the class, please just follow the slides and try to make this transformation or conversion by yourself. Right? It's relatively easy. Okay. So again, from the multivariate Gaussian distribution, we can see the difference between the commonly used form and the exponential form, right? So in practice, right, in most often cases, we're going to use mu and sigma, which are called mean parameters to represent a Gaussian distribution. You rarely use eta 1, eta 2 to represent your exponential family. When you convert it into exponential form, the form changes a lot, right? But obviously, there is a relationship or mapping between your mean parameters mu, sigma, and natural parameters eta 1, eta 2. Right? So later we'll talk about how do we get this mapping. Right? And also, there's an insightful connection between the two types of parameters in terms of feature information matrix, which we're going to discuss later, right? When we talk about the variation inference. Right? And this connection exhibits the essence of so-called mean field variation inference and stochastic variation inference. Right? Okay, so now let us look at a few important properties of the exponential family. So let us take a close look at this normalizer. So what if we take logarithm, we take the gradient of log normalizer. The gradient is taken with respect to the natural parameter. So that means I'm gonna take the gradient of my log normalizer. I want to see what happens. So we know that when we talk logarithm, take the gradient of logarithm according to the chain rule, we're gonna first take the inverse of the z eta, and then take the gradient of z eta, right? And according to the definition of z eta, we know it's normalizer, so it's actually an integration of the numerator, right? So it's h of x e to the power of ux transpose eta d of x, right? So then if we take the gradient of this guy, right, it is to say I'm going to take gradient over this integral, right? And in many cases, right, we can exchange the order of the and the gradient. That means move the gradient at the integral. Okay? So if we move the gradient inside the integral, so you see that because it's a gradient, take this, yeah, it's a gradient with respect to right, h of x is constant to eta, so it's constant factor. You just move it out. Then you take the gradient for this exponential term. So you know that gradient of exponential term first the exponential term itself, and then you take over the exponent, right? The exponent is a linear form to the eta, right? It's dot product between eta and the u of x. So its gradient will be u of x. Right? So what can we see? What can we observe? We can see that this part is the same as the original numerator, right? The only difference that in the integral, you're going to multiply it with u of x, right? So if we do one step further, right? So remember your gradient of log normalizer is the gradient of z over z, right? If you divide it by z eta, right? So you're gonna divide it by z eta here. What can we observe? So to be more clear, right? What can we observe? So what's this guy? There's no one. Look at here, right? It's here, right? Okay. So look, h of x e to the power of mu ux transpose eta, which is here, right? You divide h by z of eta here, right? So you can see that now in the integral, you actually multiply the probability density of your x, right? Right? And then you integrate with u of x. What does it mean? You multiply, you integrate the probability density with some function of the random variable. What does it mean? Yeah, it's expectation, right? It's the definition of expectation, right? For any probability density for x, right? So if you multiply, you integrate probability density with the function of x, right? So this will be expectation of fx, right? So now we can see that this essentially gives us the expectation of u of x under this exponential family distribution, right? So you can see that the gradient of the log normalizer with respect to natural parameter is actually the expectation of the sufficient statistics. And the expectation of the sufficient statistics really linked to the mean parameters, right? So remember, for Gaussian, the sufficient statistic will be x and x transpose, right? So take expectation will be mean and the variance plus mean transpose, right? So this really linked to the mean parameters, and this link back to the natural parameters. That's how the natural parameter and the mean parameters are linked. Does it make sense? That's one nice property, right? Any questions so far? Everyone's comfortable? Right? Yeah, if you still feel a little bit unclear, don't worry. You just do this by yourself. You'll see that. Right? Just um, just the ordinary derivation and take the gradient, apply chain rule, you'll see this. And even interesting property is that if you further take the gradient over the gradient of log normalizer, namely you take a Hessian matrix of the log normalizer, it will give you the covariance matrix of the sufficient statistics. Remember, sufficient statistics in general can be viewed as a vector, right? And this guy, you take the Hessian of the log normalizer or second derivative, it will be a matrix as well. So the results just tell you the second order derivative of the log normalizer gives you the covariance matrix of the sufficient statistics. Okay? And this has been left as an exercise for you in homework 1. So now let us consider, like, in the exponential family, right? How suppose we have observed a set of ID observations. How can we do the estimation of the natural parameters? Right? Suppose we have observed like n ID observation x1 to xn. How do we estimate the natural parameter eta? As euro, we just write down the joint likelihood, right? We take a logarithm, we maximize the joint likelihood, we estimate the parameter eta, right? It's very mechanical, right? So if you write down the joint likelihood over this n observations, you're gonna go over big N examples, right? So you multiply the likelihood together. That means, denominator, you multiply the normalizer for big N times, and then in exponential term, because for each example, you got this dot product, right? Eta transpose u of xn, right? But you have now big N examples together. You just multiply them together in exponent and add them together. So you got eta transpose, the summation of the sufficient statistics over all examples. And then you take a logarithm, and because h of xn is constant to eta, you can just throw it away, right? So you take a logarithm, it gives you minus n logarithm z of eta and log exp cancel. Then you got eta transpose the summation of the sufficient statistics over the big examples. And next, we're gonna set the gradient of the log normalizer to be 0, right? So if we do this, right, that means we take this gradient, we set to be 0, right? And we set to be 0, we can see that the gradient for log z eta essentially is equal to the average of the sufficient statistics over the big N examples. This is a we can do some simple calculus, right? So this is a logarithm z of eta plus, because you take this eta transpose, right? You take the gradient of eta that just disappears, just leaving its coefficients, which is n from 1 to big N and u of xn. If you set it to be 0, right? And now you just move it to the right, right? So you got here, right? And put minus n over here. That's where we get, okay? So then we can observe that for the MLE estimation, right? The MLE estimate of eta is obtained if you take the gradient for log normalizer to be the average of the sufficient statistics over the training examples. And remember, the gradient of log normalizer is actually the expectation of sufficient statistics parameterized by eta, right? This just tells us that, okay, if you want to get MLE estimation, you just set the mean of the sufficient statistics of your exponential family distribution to be the empirical mean of the sufficient statistics in the data. Right? So this guy is actually an empirical estimate of the mean of the sufficient statistics. Does it make sense? Right? In general, it's like, okay, if I want to estimate what is the chance that I see ahead when the toss of a particular coin, right? Or what should we do, right? I just toss the coin for 100 times, right? And I look at what's the result for each tossing, right? And it may be 60 times heads and 40 times tail. And then I take empirical estimate of my mean, which is 60 over 100, which is 0.6, as my estimate for the mean of the distribution. Okay? This is the same as what we commonly use to estimate distribution parameters, right? But now we generalize to the exponential family. In exponential family, how do we get MLE estimation? We just set the mean of the sufficient statistics to be the empirical estimate of this mean from data. Any question? Is everyone comfortable, or is this too straightforward? Any question? Just let me know. Okay, so let me emphasize it again, right? So this guy can be viewed an empirical estimate of the expectation of UX, right? You got UX1, you got UX2, you got Xn, right? If I want to get a expectation of U of X, right? So I got n such kind of examples, right? I just do the average. This is my estimate of their expectation, right? So now this result just tells us, okay, if you set your empirical estimate of UX to be the mean of your distribution, then that's it. You have already obtained your MLE estimate. Okay. That's the idea. Okay. And this is what MLE framework reflects, right? It's very similar to many other MLE examples, right? If we toss a coin for 100 times, right? We know that, okay, we just look at the ratio of heads, right? Which is, for example, 0.6, right? 60 over 100. This empirical estimate of the probability you see the heads, right? Because it's an indicator, right? It's an indicator you want to say what's the expectation of this binary variable. The binary variable is whether you see the head. You see the head of the coin, right? You run it 100 times, you got 60 heads up, so you get so empirically your empirical average is 60 over 100, which is 0.6, right? And if I set 0.6 as my Bernoulli parameter mu, right? That's my MLE estimate. And similarly, we can generalize this observation to the exponential family. For the general exponential family, if you want to do the MLE estimate, we just calculate the empirical estimate of the mean of the sufficient statistics and use that to parameterize my exponential family. That's it. Right. Again, if you still feel a little bit confused or uncomfortable, that's natural, because you might have never seen this kind of formulation, right? But after you doing this kind of derivation, you see that. Okay. This is called empirical mean, right? So, what is the conjugate prior to the exponential family? Right? What's the general conjugate prior form? Right? So, suppose your likelihood of x follows a distribution in the exponential family, which is this form, right? So if you want to find the prior of eta, which is conjugate to this likelihood, it will have this form. So you can see that the conjugate prior of eta, the natural parameters, has two parameters. One is this kappa and this nu, right? So the form is that, okay, in a denominator, I take the same form of z eta as in the likelihood, but now I take a power of nu. And in the exponential form, right, in addition to this dot product between eta and the kappa, and also multiply a skew nu. This is a general conjugate prior form to this exponential family. So to see this, let's try to compute the posterior distribution of natural parameter eta. Right? So we know that the posterior distribution of eta, given the theta x and given the prior parameters kappa and nu, is proportional to the prior multiplying with the likelihood, right? If we just merge the term together, we see that it is proportional to, in the denominator is z eta to the power of nu plus 1, right? And in the exponent of the exponential term is eta transpose nu times x, which is come here, plus the sufficient statistics u of x, right? Does it make sense? It's just multiplying these two, the prior and likelihood here together and just merge the terms. So next, we're gonna look at if it has a consistent form of the prior, right? So it's relatively straightforward to see that, okay, this guy, we see that in the general prior form, it should be, in the denominator, should be the z eta to the power of something, right? So we know that it's to the power of nu plus 1. And in exponent form, you got eta transpose with something and then multiply with something, right? So we know that the scale which you multiply should be nu plus 1. So that means in the outside, you should multiply with nu plus 1. And then in the inside of the parentheses, you should divide it by the nu plus 1, right? To match this guy, right? You got nu eta transpose kappa, right? So the new kappa now is here. Is nu x, a new kappa over nu plus 1 times kappa plus 1 over nu plus times u of x, right? And then this scale parameter is just nu plus 1. Right? So we can observe that first, this nu parameter increases by 1. You can view it as a pseudo count of the examples, right? So in the prior, you can assume that, okay, in my prior space, I believe that my example has been observed for new times, right? I've observed new examples, so it's pseudo count. And then after I really observe one example, so I increase my pseudo count by 1, right? So I got nu plus 1. And then in another parameter, kappa, so you can see that after the posterior update, I essentially combine my prior parameter kappa with the data information, right? But this is weighted combination, right? Kappa is weighted by nu over nu plus 1, and the new data is weighted by 1 over nu plus 1, right? So you can see this is where the data information shoves in, right? And of course, here you only observe one examples. So it looks like your data information doesn't take too much weight here, right? But if I observe many examples, imagine this part can take a lot of more weights, kind of dominate this part. Any question? Okay. Yeah, nu can be viewed as pseudo count, right? So now we have finished the introduction of the exponential family and a bunch of very commonly used distributions. We're going to revisit those distributions and the general exponential form from time to time, especially when we talk about different approximate inference algorithm or specific probability model. They're so important, so fundamental, and so common use. So we have to frequently use them. That's why we should spend quite a while to discuss with. Okay, so what do we expect that you need to know after this discussion of this section is that, okay, you should know what are the conjugate priors, right? What's the definition and what's the motivation of conjugate priors? Unfortunately, it's mainly from the computation convenience. It's not from modern perspective. Right? And what are the conjugate priors to commonly use likelihoods? Right? For this, for example, what is a conjugate prior for the polynomial likelihood? We know it's beta distribution. For the categorical likelihood, we know that it is Dirichlet distribution, right? For Gaussian, for the variance, for the inverse variance, it should be gamma, right? For the inverse covariance matrix, it should be the Wishart distribution. Right? You should have some kind of concept on that, right? And you should know what's the definition of an exponential family, how to convert the existing distribution into the state. Okay? It's really relatively easy, but you might feel uncomfortable at the first sight. Right? And you should know what is properties of the exponential and the general conjugate priors to the exponential family. Okay, any questions so far before we move to the next topic? Great. Next, we're going to talk about some necessary and basic concepts in information theory, which we're going to use in our probabilistic learning, especially in the inference technique. So let us start with some discrete random variables. So in a coding theory, right, which are often used in electrical communication, right? There's one critical problem is that, okay, how do we represent the information contained in some random variables? Suppose these random variables are just discrete. So half a century ago, or more than half a century ago, when Klaus Shannon think about this problem, right? He wants to work out or design some kind of function which can represent the information that should be contained in a random variable. And you can use this measurement function to compare the information contained in different random variables. Right? So naturally, he thought that, okay, suppose we define this information function by h. X is a random variable, right? So I thought that, okay, actually first those measurement function or information function should be non-negative. Right? And second, if x, y are independent, like two independent variables, then their joint information should be the information of x plus information of y. Right? This is very natural. Right? So by looking at this basic two properties, like he thought this should be necessary. We'll define any proper measurement function about the information, right? It links to the probability density, right? Because x is a random variable, and actually it should be first characterized by some probability or probability density, right? So if we look at the probability density, so first we know that p of x, right, must be non-negative, right? And second, we know that if x, y are independent, then their joint probability should be p of x multiplying with p of y. So it looks like it's straightforward that why not we just define my information function of x as negative logarithm of the probability of x. If we do such kind of definition, it immediately satisfies both properties, right? So first, p of x is less than or equal to 1. That means negative logarithm must be a non-negative, right? And second, if x, y are independent, right? We know that their logarithm of the joint probability must be the logarithm of p of x plus logarithm p of y, right? Of course, you take negative, you take minus sign, it won't change, right? So immediately get these two properties. One is non-negative, and second is addition, right? Then Shannon just defined his own information function of x as negative logarithm of probability of x. Does it make sense? Okay. That's that is how he was motivated for this, and this is how right now, like most information theory definition. But you can definitely define your own information measurement function. Like, this is not the only definition. Right? You can propose other information function which can also satisfy these properties. That's totally fine. Right? Here we just emphasize the most classical and most commonly used way to define your information function, right? And this information function is also called the entropy. Right? It's the entropy function, or entropy of x. And then, because the information function here, h of x itself, it depends on x, right? X is a random variable. That means it is associated with some random experiments. So different random experiment outcomes will have different output of x, right? Different values of x. So h of x itself is still a random variable. And we want to, if we want to look at the total information all the holistic information about this particular random variable x contains, right? Remember, x takes multiple values. And naturally, we're going to take an average, right? We're going to take the average of this information function of h of x in terms of different choices of x values. That's how we define entropy, right? Entropy is the expectation of the information function h of x. So if you write it out, it's a summation of negative p of x logarithm p of x, right? It's expectation of x negative logarithm p of x. Any question? Okay. So from a coding theory, entropy is also an average code length. That means, okay, if I want to code, I want to design some binary code, right? Bits to represent a particular random variable. What is the average length that I can use to represent a random variable, which we just listed for your reference, right? We're not going to go deep into that, right? So entropy, as the name suggests, essentially reflects uncertainty, right? So here's the entropies of two random variables, right? So those histograms just shows how these random variables, the values are distributed. Right? So you can see that the more concentrated this random variables distribution is, right, the less the entropy. Why? Because the more concentrated of your distribution, the more certain I know where you're going to disappear, where you're going to appear, right? Where your value should be, right? So I'll be more certain about the values. That means my uncertainty is small. It gives a smaller entropy, right? And on the other hand, the more spread your distribution is, the less likely that you're confident about what's the values of your x can take. Then your entropy is large. And in other words, the information the random variables it contains is more. Right? Then a natural question is like, suppose we're given a discrete random variable, right? Suppose this random variable has only m possible values, right? We want to ask what kind of distribution can give you the maximum entropy or maximum information. We actually can solve this problem. How do we solve that? We know that, okay, because it is discrete random variable, right? So actually, it is just parameterized by the probabilities that your x takes 0, 1, 2, 3, like m, right? So if we just write down its entropy is in this form, right? Is a weighted average or just expectation of negative logarithm of p of xi. P of xi just means x takes the ith value, right? And then we need to consider that the summation of those probabilities must be 1, right? That's why we need to introduce the Lagrange multiplier. Then we just solve this problem, right? We just maximize this entropy and solve this problem. We take the gradient, set the gradient to be 0. You can see that if you want to get maximum entropy, your distribution should be the uniform distribution. Right? Namely, the chance that x takes each value should be the same, which is 1 over m. And this is also reasonable, right? When I would be most uncertain about this random variable, it is when the chance that this random variable takes every different value. I don't know. I don't have any preference of which value it should take. Right? On the contrary, you can imagine that if the probability mass concentrated only on one value, right? So I know that the probability that for x takes one is one, right? The probability that x takes all the other values is simply zero. Then I'm uncertainty. I don't have any uncertainty, right? I'm pretty much sure. Okay, you give me x, I know it's value must be one, right? No, there's no uncertainty. In other words, there's no information now because I know when I know the value. So entropy is naturally defined on discrete randomness, right? And its definition, its derivation all looks good and comfortable, right? Now let's try to extend it to continuous variables. How do you do that? The idea is to first discretize the continuous variables. Right? We want to extend the entropy definition in a discrete case to the continuous case. So we first discretize the continuous variables into like discrete random variables, and then we try to take the limit and make it more and more toward the continuous case and see if eventually we get some same reasonable and good definition. Right? How can we do that? Right? Suppose it's a density of x, right? We know x is continuous, right? So to convert x into a discrete random variable, we're going to divide the value of x into bins of delta. So delta here is the bin size or bin length, whatever, right? So then I can represent x, right, in terms of a discrete random variable, right? So y, right? So y, you can take values like 0, 1, 2, 3, and perhaps like many, right? It's infinite but countable, right? So p y equals to I just means y equals to I means x falls in the region I delta and I plus 1 delta, right? This just tells me, okay, if I will, the choice, the values x can take, right? So it's hard to directly measure what's the information it contains, right? Then I just look at, okay, what if I just look at the events that x value falls in some specific region or specific bin, right? So that means x can take the values in bin 1, bin 2, bin 3, bin 4, and so on. And then I convert x into a discrete variable y. And then I can try to compute the entropy of y. Does it make sense? Right? And of course, the larger the bin size is, means the larger the delta is, the coarse the y is, right? It is kind of coarse approximation of x. However, if we keep decreasing delta, right? Keep decreasing delta, when delta converts to 0, then your y actually converts to x, right? So what to look at in general, like for any given delta, what is your entropy of y? And then just take a limit. If delta goes to 0, what happens to your entropy in terms of delta, right? That's the idea. So to compute the entropy of y, right? We know that y equals to I. That means x falls in this i's bin, which is in the region I delta and I plus 1 delta, right? So I want to know this probability, right? This probability essentially is the this integral, right? This integral of p of x over the ith bin, right? And we know that according to mean value theorem, for any specific thing, right? This integral is actually the area, this area of density curve on this bin. It is equivalent to it is equal to some value, right? Some position in this bin, say xi, right? And you multiply P of xi over the bin length or bin size. It's the same. So we can represent the probability that X falls in S bin by some probability P of xi times the bin size delta. Right? Now just shove this result into the computation of entropy of Y. Okay? So you see that it will give you a summation over all the bins, right? And minus P of xi. Remember, xi is some position inside each bin, right? Times logarithm times the bin size delta times logarithm P of xi, and subtracted by logarithm of the delta. And actually, like, because we will like, okay, the discretized version of X with respect to delta as a rough approximation of the entropy of X, right? And we know that only when delta goes to 0, then your discretized version is equivalent to the original continuous version X. Right? So naturally, want to say, okay, what if delta goes to 0? What happens here, right? And unfortunately, we got a constant term, logarithm delta here. So the bin size goes to 0, then this guy goes to infinity. Like minus logarithm delta, right? Delta goes to 0, logarithm of delta goes to minus infinity, and minus logarithm delta goes to infinity. So actually, if you follow the definition of entropy in a discrete case, it won't work for the continuous case, because the continuous case for entropy is simply infinity. That's reasonable as well, because you can imagine, because continuous random variables, and it can take infinite many possible values, right? And in principle, it indeed contains infinite amount of information. But here, we want to have some more practical, useful measurement, right? Even for different continuous random variables, we want to compare their difference in terms of their information contained, right? So we look at the first term. Let's just throw out the second term that leads to infinity. Right? Let's just look at the first term. Right? So the first term, this summation over P of xi times delta times logarithm P of xi. When you take limit of delta goes to 0, who can tell me what does this mean? Yeah. And we all have learned from our calculus course, right? This is called Riemann integral, right? It's called Riemann integral. Right? If you can recall the definition of integral is essentially a limit of the summation, right? And there are two types of integral: the Riemann integral and sorry, I forgot another name, but it's that integral is more well posed. If you talk about matter theory, you would use that kind of integral. But the Riemann integral is mostly into definition of the integration, right? So if you want to do some integration of fx, g of x, right? So what you need to do is that, okay, I'm gonna partition the domain of x into many small bins, right? And then for each bin, I can pick up arbitrary function value in this bin and multiply with the bin size delta and multiply with integration function g of x, right? And if the limit that when bin size goes to infinity of this sum exists, then we call it this is an integral, this is a Riemann integral, right? And it's called this integral exists, right? But be careful, there are cases where Riemann integral doesn't exist. So that means it is ill-posed, and you have to consider another type of integral. So, so when you take delta goes to 0, now it becomes Riemann integral, then essentially it becomes an integral of the probability density P of x times logarithm P of x and dx, right? So this basically means that, okay, when delta goes to infinity, this one is real as P of x times d of x, right? And now you take the summation, you replace summation by the integral, right? So now we get our definition of the continuous random variables H of x as negative integral of P of x logarithm P of x and dx. So this is where is how our commonly used entropy comes from. It's kind of consistent with the discrete case, right? Discrete case is a negative summation of all possible values x can take a logarithm of P of x, right? You can see that there seems no difference, right? The only difference is that, okay, I'm going to change the sum to switch the sum to the integral, right? But the meaning has a lot of difference. For the continuous random variable, this is called differential entropy. It's not the true entropy. It's just the differential entropy. It just tell you, okay, by looking at this term, you can differentiate the amount of information contained by different continuous random variables. But if you want to be consistent with the original definition entropy in the discrete case, actually the continuous random variables, any continuous random variables contains an infinite amount of information. Any questions so far? Okay. And also be careful, differential entropy can be negative. It's not like the discrete random variables. This guy will always be non-negative because each P of xi must be between 0 and 1. Right? So this guy is guaranteed to be non-negative. But this one, this is density, right? The density can be very large. It can be much bigger than 1. So you do this integral, it can be negative. Right? So don't be scared if you get negative entropy for some continuous random variables. It's completely normal. Before we talk about next word, any question? Okay, so now a similar question to the discrete case, right? Suppose we're given a continuous variable x, right? Continuous random variable x with a mean mu and variance sigma squared. Which distribution gives the largest differential entropy? We can still solve this problem by optimization, right? So first, we need to know that for any valid density, right? We need to ensure that, okay, its integral from minus infinity to infinity is 1. And here we put constraint that the mean must be mu and the variance must be sigma squared, right? And then we just maximize the differential entropy with respect to the 3 constraints here, right? That means we need to add 3 Lagrange multipliers, right? We can solve this. It's not hard to solve. And the result turns out to be that the Gaussian distribution with the given mu and variance sigma squared will give you the maximum entropy, maximum differential entropy. Again, I highly suggest you to try to do this by yourself, like to practice on and also deeply understanding of this definition of entropy and differential entropy. So, given the definition of entropy, we can actually extend to the so-called conditional entropy. Right? So, conditional entropy tells that given x, how much information is left for y. Right? It is very intuitive to represent in terms of graphs, right? Suppose this is around the variable x, and this is around the variable of y, right? We use the area of those circles to represent the information contents in each variable, right? So conditional entropy just tells or measures, right? Given x, right? What is is the remaining information contains one, right? That means you just include the overlapping part and look at what's the remaining area of one. Okay? So the definition is as follows. So it's negative integral and P of the joint probability x and y. And now, in the logarithm part, it's the logarithm of conditional probability of y given x. And then you integrate with y and x. So if I replace the conditional probability in the logarithm part by P of yx, what's that? What's that? It's drawn entropy, right? It's just drawn entropy, right? If you write it as P of xy, logarithm of P of xy, dy, dx, it's just hx and y, right? This is definition, right? But here, if you use conditional probability in the logarithm part, it becomes conditional entropy. There's a very intuitive connection between the entropy, drawn entropy, and the conditional entropy. That is, the drawn entropy is the marginal entropy of x multiplying the conditional entropy of y given x. Okay. And this can also be represented by these circles, right? So know that the drawn entropy of x and y would be the area of x and y, both x, y covers, right? And then it can decompose as, suppose this is x, this is y, right? So it's area of x, which h of x, right? Plus the remaining area of y, which is conditional entropy. Okay? So now I want to ask you guys to prove it by yourself, right? Just leveraging the definition. And then KL divergence. So KL divergence is actually the most important information measurement we're going to use in our progressive learning. Entropy is often important, but it's less important than KL divergence. So what is KL divergence? KL divergence is defined as follows. So this measures the difference between two distributions, P and Q. Right? This is computed as follows. If you compute the KL divergence from P to Q, it just means you're going to integrate P of x and then logarithm of fraction between Q over P and times D of x. And then you need to put a negative sign here. Okay. So you can roughly view as a measurement of the difference between two distributions. Remember here, I use 2 points to represent two distributions. We can use KL divergence to measure their difference. However, this is not a valid distance metric. So that means if you compute KL divergence from P to Q, it usually is different from KL divergence from Q to the P. So you can see this from natural, right? If you want to compute KLQ from P, right? So now in the integral, you got QX logarithm PX over QX, right? So P over Q and then times D of X. You can see the form changes a lot, right? The part of the distribution you're gonna density you want to integrate with now switch to Q of X. So really, these two things are different. Right? They are different. But it's still a very commonly used measurement is to reflect how far away between the two distribution P and Q. Right? So why is it important? Because when we want to approximate the posterior distribution, as we said, right, a common strategy is to pick up a simple distribution to approximate the complex target posterior distribution. I'm going to specify a range of simple distribution like an exponential family. Then I want to find out the one best approximation. And how do we measure the best approximation? I want to minimize the QL divergence. Okay, so let's stop here today. Let's continue on Thursday.
I kind of connect to check the class. So I wonder, because I follow the chapter of the